Welcome, everyone. For today's prep, we're going to start looking at improper integrals. And the case we're going to start with is the case where we try to integrate certain functions over an infinite interval. All right, so let's kind of start back with where we started with integration, and that was the fundamental theorem of calculus. So let's suppose that we have a function f, and it's continuous on a closed interval from a to b. And we know how to calculate the definite integral for that. And it involves doing the antiderivative. So we find the antiderivative of our function. So we're going to let, in this notation, capital F be our antiderivative. And then the top number gets plugged in, we subtract, and then the bottom number gets plugged into our antiderivative. All right, so there's kind of two things here where we can run into issues. So first, the function that we're integrating has to be continuous in order for this theorem to work. And we're going to see what happens if we kind of relax that condition a little bit. It turns out in a lot of cases, we can still calculate this definite integral, but we have to be a little bit careful. So we're going to investigate kind of two types of improper integrals. So the second type we'll look at is the case where the function f has a discontinuity. Or maybe more than one discontinuity. So, it doesn't just have to be one. So again, just remember, discontinuity is a place where the left-hand limit, the right-hand limit, and the function value don't all match up. So there's like a hole or a jump or a break in the graph. All right, so that's going to be one of the cases. We are going to see what happens if we have a discontinuity. The other case has to do with kind of like the size of our interval here. So in the statement of this, we're looking at a closed interval. So the interval is closed, meaning it contains both of its endpoints, and it's finite, so it's bounded in either direction. What we're going to be looking at, and this is what we're going to start with today, is what happens if we have an unbounded interval, an unbounded closed interval. So the forms that we're going to be looking at are intervals like a to infinity or minus infinity to b or minus infinity to infinity. So we're going to be looking at, so if there is an endpoint, it's still going to be included. What happens in these cases? So there's kind of two requirements to this theorem, and we're going to see what happens. Sometimes we'll see that the integral doesn't exist. It's undefined. But sometimes it actually is defined. So we're going to look at this. So let's start with the first case that we're going to consider. And this is where we're going to be dealing with an improper integral. We're still going to keep x, or our function f, to be continuous. And the interval that we're looking at in this case is, we're going to be looking at the interval from a to infinity. So this is the first case we're going to consider. And so we put infinity as kind of one of the limits of integration. Now, when we do this, we want to remember that infinity is not actually a number. So we're not going to be plugging infinity into our antiderivative. How we're actually going to handle that infinity is we kind of have to sneak up on it. We have to approach it. So Again, you want to think of infinity not as so much a specific number, it's kind of like a location that you're headed towards. So the way we're going to calculate this type of improper integral is the first step is we're going to rewrite it as a limit. So we'll do the limit as b approaches infinity, and then it becomes the improper, or the integral from a to b. So our step here is we're going to take the infinity off of our integral sign, and we're going to approach it. We're going to do a limit. All right, so when we calculate limits, there's kind of two things that can happen. Either the limit gives us a value or it doesn't. So when we calculate this limit, if we actually get a value, we're going to say that our improper integral is convergent. And when we calculate this limit, if we get that it doesn't exist or is infinite, then we say it's going to be divergent. The improper integral is divergent. All right, so how to interpret this as an area? So, if we remember back, definite integrals relate to the area under the curve. So when we're trying to calculate the integral, the improper integral from a to infinity, the idea when we rewrite it as a limit like this, the idea is that we're still going to be starting our integration at kind of the endpoint A. So we're still going to have this starting point for our integration. So this is A. And the idea with that limit is we're kind of just putting an arbitrary endpoint to our region. So this might be like B. So what we're doing when we calculate this definite integral going from A to B, this improper integral, or that definite integral, is giving us this shaded region where we end at B. And by calculating the limit, essentially what we're doing is we're moving that one endpoint. So we're going to look at what happens as we slide this endpoint further and further to the right. So that's what the limit actually does. So we're sliding the endpoint further to the right. All right, so the question is, it seems very plausible that any function that we're looking at, if we're trying to figure out the area under the curve and we're looking at a region with an infinite width like this, we'd expect the area to be infinite. Turns out that that's not always the case, surprisingly. So we're going to look at, in the first example, we're going to see how to do these types of calculations. So the function that we're integrating is e to the negative 2x, and we're looking at the closed interval starting at 0 and going all the way to the right. So the interval in this case is the interval from 0 to infinity. So this is an unbounded interval, and that's why this is considered an improper integral. This is not a finite interval. All right, so how do we actually do this? So let's start by just writing down the integral we're going to try to do. And the very first step for these improper integrals is we rewrite it as a limit. All right, so we're going to make our upper limit. We're going to peel off the infinity here, and we're going to look at the limit as b goes to infinity. So again, when we deal with the infinity, infinity is not a number, so we can't just plug it in to our function. So instead, we have to approach. We have to sneak up on infinity. So the first step is we rewrite this as a limit. And we keep the function the same, so e to the negative 2x. All right. So once we've rewritten this as a limit, then we do the definite integral part just like we normally would. So this section right here, or this piece of the notation, this is just a regular definite integral now. So we can use all of our old strategies. So the next step is we find the antiderivative. And we know sometimes the antiderivative is difficult to get. But in this case, e to the negative 2x, this is just one of our special k-forms. So the antiderivative there is going to be, we keep it e to the negative 2x, take the constant k, flip it, put it in front, so we end up with a negative 1/2. So that's our antiderivative. And then we're going to evaluate this antiderivative from 0 to b. Now, we haven't dealt with the infinity part, so we still need to keep writing our limit sign all the way in front of this. And once we get our antiderivative, the next step is to evaluate the antiderivative just like we normally would. So we're just evaluating like usual. All right, so let's see what we get. So top number gets plugged in first. And again, we still haven't dealt with the infinity, so we need to keep writing this limit sign. So top number gets plugged in first. We end up with negative 1/2 e to the negative 2b. Then we subtract, and then we plug in our lower bound. So we plug in the 0 here. And when we plug 0 in, we're going to get e to the 0, which is just 1. And we're subtracting a negative, so this will become positive. So a double negative. So it'll be plus 1/2. All right. So at this point, we've rewritten the improper integral as a limit. We found our antiderivative of our function, kind of like regular. Then we evaluated our antiderivative, just like usual. And you want to look for things to simplify. So before we actually calculate the limit. So, we don't necessarily need to do anything here. This is pretty good. I think terms with negative exponents, though, when we're going to go calculate the limit, it's better to write them as a fraction. So I'm just going to rewrite this. So we're still going to have our limit b going to infinity. And I'm just going to rewrite this a few separate ways. So I'll take the positive term, put it first. And then we're subtracting. And rather than have a negative exponent, I'm going to write that exponential as a fraction. And I just think it's easier to visualize when we do the limit. All right, so once we've simplified and rewritten things, now we're ready to actually calculate the limit. And what we have here, so that's our final step. Calculate the limit. All right, so what happens? B is the thing that's going to infinity. So the 1/2 here is just going to stay 1/2. And then this fraction is going to be a c over infinity form. So if b is getting really large, the exponential here is going to get really large, but then we're dividing by it. So this is going to be a c over infinity form. So what we end up with is 1/2 minus 0, which is 1/2. And again, this is a c over infinity form. And those go to 0. And because we found that this value was an actual number, not infinity or didn't exist, we say that the improper integral is convergent. So how do we interpret this value here? Well, the interpretation, if we go down to the graph of our function, is that the area under e to the negative 2x is equal to positive 1/2. So starting at a equals 0 here and going forever to the right, that total area is equal to 1/2. And I guess it kind of seems plausible here because even though the width is infinite, the height of our function, once you get past this section, the height of the function gets very small. So it's almost like when we're doing this improper integral, we're kind of slicing this little really thin region up, and it actually just fits. We could fit all the pieces into just a nice finite rectangle, finite box. So the total area of all this, still kind of surprising though. You'd almost expect an infinite width to give infinite area, but it's not the case here. So we're going to see cases where sometimes this area though is infinite. So we'll see those in class. We'll see you then. Bye-bye.